Chapter 5, Module 4, Retracts and Deformation Retracts. In this module, we shall discuss several subspaces of topological spaces which play a very important role in studying homotopy theory. So far as homotopy theory is concerned, we shall see later on that these spaces are very important. We begin with defining a topological analog of what we call projection operator. A subspace A of a topological space X is called a retract of X if there exists a continuous function R from X to A such that R restricted to A is the identity function on A. That is, for all A belonging to capital A, RA is equal to A. Such a map R is called a retraction. A retraction as defined above is always a surjective map. However, one may equivalently say that a retraction is a map R from X to X such that R square is R. So, composing R with R gives me back R. Certainly, in this case, if we take A as the image of the map R, then it is a retract of X, but this map R is not surjective except for the case when R is the identity map. Now, the following is a trivial example of a retraction. If we take a topological space X, pick a point x0 from capital X, consider the subspace capital A as the one pointic set x0 and consider a constant map Cx0 which maps the topological space X to the space A, then Cx0 is a retraction, and in that case capital A becomes a retract of capital X. From this example, it is easy to see that a space may have several, maybe infinitely many retracts. In fact, any singleton set of a given space X can be viewed trivially as a retract of capital X. But we are actually interested in a special type of retract which we call deformation retract. Let us take a subspace A of a topological space X. We call capital A deformation retract of capital X if there is a continuous function capital H from X cross I to X such that Hx0 is X and Hx1 belongs to capital A for all X belonging to capital X, and Hat is equal to A for all T belonging to capital I, then this capital H is a homotopy, and this homotopy is called a deformation retraction. So, we call the space, the subspace A deformation retract of capital X, and by means of the homotopy that deformation retract is obtained. So, that way the homotopy is called a deformation retraction. Equivalently, deformation retraction is a continuous map F from capital X to A, which is a right homotopy inverse in X of the inclusion map I from A to A, which is relative to the subspace A. That means if we consider the composition I composed F and consider the identity function, then I composed F and the identity function are homotopic relative to the set capital A. Now, how do we establish this equivalence? If a homotopy capital H exists, then F from capital X to A given by Fx equal to Hx1 satisfies the condition I composed F homotopic to identity. On the other hand, if there exists a continuous function F such that this condition is satisfied, then there exists capital H so that capital Hx0 is x, capital Hx1 is inclusion composed F evaluated at x, which is inside capital A for all x belonging to capital X. So that homotopy H is such that for every value of t, Hat is equal to A, and that is true for all A belonging to capital A. Of course, a deformation retraction is a retraction. But the question is the converse true in general? Every singleton is a retract of any space. And so, in particular, a retract of a non-path connected space as well. So, there are numerous examples of retracts, but these are not deformation retracts always. Now, we see one example of a deformation retract. Suppose we take the punctured plane R2 minus 0 and we take the unit circle S1. We define a map F from R2 minus 0 to S1 given by Fz equal to Z by mod Z. Then this function F is of course a continuous function, and if I take the inclusion map from S1 to R2 minus 0, 0, then this I is an inclusion map such that F composed I is equal to identity on S1. Now, let us define a map H from R2 minus 0, 0 cross I to R2 minus 0, 0 by Hzt is equal to 1 minus t into z plus t times z by mod z. Then this H is continuous. Hz0 is z, which is identity on S1 evaluated at z. Hz1 is equal to z by mod z, which is inclusion composed F evaluated at z, and Hat is equal to A for all A belonging to S1 and T belonging to I. Hence, this capital H is a deformation retraction. So, what I get is that the punctured plane R2 minus 0, 0 and the circle S1, if these two spaces are given, then S1 is a distinguished subspace of R2 minus 0, 0. It is the deformation retract of the punctured plane. Intuitively, given a topological space X, if we shrink the space and it falls onto a subspace A of the given space X, and in this process of shrinking, if the subspace remains unaltered, then that particular subspace is called a deformation retract of the given space X. And this process of squeezing can be said that that is the deformation retraction. Now, we may feel that there are spaces which can be shrunk in various ways. That means, given a space X, we can shrink it to get a subspace A, and in this process of shrinking, the space A remains unaltered. At the same time, given the space X, we can find some other subspace B such that if we shrink the space X and fall into B, the points of B remains unaltered. So, the conclusion is we feel that there may be more than one deformation retracts of a given space X. Now, we give an example where we show that a space may have two different deformation retracts, but those deformation retracts, if we call them A and B, then A is not a deformation retract of B, nor B a deformation retract of A. Now, we give an example. We take the theta space and figure 8 space. We show that these two are deformation retracts of doubly punctured plane. The following diagram shows how a doubly punctured plane deformation retracts to a figure 8 space. Now, figure 8 space looks like this. It looks like a figure of 8. We start with a doubly punctured plane, that means a plane where we are removing 2 points P and Q. First of all, we are drawing a circle around these 2 punctured points to get a figure like this, and we are allowing the points outside this circle to deform to get the circle and get the figure like this. Now, separating these 2 points again by circles and doing the same thing, we get a figure like this, and in this case, we are stretching all these points towards the boundary of the circles to get a figure of 8 space. So, stretching and squeezing is not altering this shape. If we draw 2 circles here and apply these techniques, then R2 minus those 2 points, that is doubly punctured plane, will deformation retract to a figure 8 space. Similarly, do the same thing. Instead of drawing 2 circles around the punctured points, we draw a line to separate the punctured points. Then what we get is a theta space. We apply the same technique of squeezing and stretching to get the deformation retract of the doubly punctured plane as a theta space. Now, it is not very hard to see that the theta space and figure 8 space, these are not deformation retracts of one another. That means, theta space cannot be deformed to get its deformation retract as figure 8 space. Similarly, figure of 8 cannot be deformed without altering the points on figure 8 to get a shape like a theta space. Now, we prove a result that if C is a deformation retract of B, and B is a deformation retract of A, then C is a deformation retract of A. Now, how do we prove it? We take the inclusion maps IB and IC. IB is an inclusion map from capital B to A, and IC is the inclusion map from capital C to B. Let IB from B to A and IC from C to B be the respective inclusion maps. Then it is clear that identity function on B and the inclusion map IB, they are same for all B belonging to capital B. Now, the definition of deformation retracts says that there are continuous functions f from B to C and g from A to B such that IC composed f is homotopic to IB relative to the set C, and IB composed G is homotopic to IA relative to the set B. So, IC composed F composed G is homotopic to IB composed G relative to C, but IB composed G is small IB composed G, inclusion B composed G, which is homotopic to identity on A relative to the set C. Hence, IC composed F composed G, because composition of maps is associative, is homotopic to identity on A relative to C. This shows that C is a deformation retract of capital A. Now we show that if every singleton is a deformation retract of a given space X, then the space X is path connected. So let us take a point x0 from capital X. By definition of a deformation retract, there exists a homotopy capital H from x cross I to x such that hx0 is equal to x, hx1 equal to x0 for all x belonging to capital X, and hx0t is equal to x0 for all t belonging to capital I. Define for each x belonging to capital X a path wx by the help of the given homotopy capital H, that is wxt is equal to hxt for all t belonging to capital I. Then clearly wx defines a path joining x0 and x in capital X. The arbitrariness of the point x shows that the space capital X is path connected. Now the question is the converse true? Now it is less trivial to establish that there are path connected spaces that do not deformation retract onto a singleton. Intuitively, one may visualize this in case of a circle S1, which is a path connected space, but it does not deformation retract onto a singleton. Later on, we shall see how the concept of fundamental group helps to answer this question in a nice way. Finally, before we end this module, we just point out that in the subsequent chapters, we shall see that for constructing a fundamental group of a space, we don't need to construct the group for the whole space, but if we can find the deformation retract of the space and find the fundamental group of the deformation retract, then that serves the purpose. So that way, deformation retracts are very important in connection with fundamental groups.